In this video, I'd like to talk about special right triangles, and we want to look at two in particular. So one of these we call a 45-45-90 right triangle, where we have this isosceles triangle. We have two equal angles, and they're both 45 degrees, whereas the third angle is a right angle, since we're dealing with right triangles. And we know it's isosceles because if you have two equal angles, then the side lengths that are opposite those are going to be equal as well. So this side here and this side here, these are both equal to each other. So this is one type of right triangle that is special and shows up often. And the second one is what we call a 30-60-90 triangle. So this triangle is actually formed when you take an equilateral triangle and you cut it in half. So it's not going to be drawn quite perfectly, but we're essentially just taking an equilateral triangle where all the sides are the same length, and we're just splitting it right down the middle. So these triangles also show up quite often, and the small angle has 30 degrees, the large angle has, or the middle angle I should say, has 60 degrees, and of course the largest angle is 90 degrees. So both of these triangles show up quite often, and it's worth investigating their properties. So let's start with the 45-45-90 triangle, this isosceles right triangle. And let's take a closer look at that. And like I mentioned, this is isosceles. We know this side and this side, these are going to be equal to each other. So to look at the relationship between the side lengths, we're going to need the Pythagorean theorem. And remember, if we have some random right triangle, and let's say we know the side lengths, we can call these A, B, and C, where C, that's our hypotenuse, that is directly opposite the right angle, then the relationship between the side lengths is that A squared plus B squared is equal to C squared. So knowing this, we can look at the properties of this triangle. And let's just call these side lengths some letter so that we can look at this very generally. So let's maybe call this x, and because this side length is equal, we can call this x as well. And we want to figure out what the hypotenuse would be in relation to these two side lengths. So this will be some quantity involving x. But for now, let's just call it h for hypotenuse and try to solve for it and figure out what it would be. So if we set up our Pythagorean theorem, the side lengths are going to be a and b. And if we want to label that, we can. We can call this a, and maybe we can call this b, or vice versa. It doesn't matter here. So that we get a squared plus b squared. Excuse me, that would just be x squared again. And this is equal to c squared. And c is the hypotenuse. That's the one that's always opposite the right angle. So in this case, we get h squared for c squared. And let's simplify. So x squared plus x squared, that's just 2x squared. And since we're solving for h, we want to take a square root of each side. And the square root of h squared, those cancel, and we just get h. And over here, we get the square root of 2 times x squared, which I'll break up into a product of square roots since we have a product on the inside. So we get root 2 multiplied by the square root of x squared. And just like we had here, when we take a square root of a square, it's going to cancel. So the end result is that h is the square root of 2 multiplied by x. So in the end, we can just replace this with root 2 times x. So all three of these sides are related in a nice way where whatever these side lengths are, the hypotenuse is just the square root of 2 times these side lengths.